Yesterday we talked about, well, a little bit about minimax. Well, in the last classes we talked about how minimax works, as how it breaks down and almost like the rules or how it breaks down the game. And yesterday specifically we talked about well, how a minimax algorithm without many modifications, or for what I believe, probably non-modifications at all, would behave in a game of, well, tic-tac-toe. And talk about a better way to represent a game of tic-tac-toe. After all, there are 255,162 possible games, and meaning not just games, but a better way to represent it is as states. So there are 255,162 possible states in a game of tic-tac-toe. And so, well, I said there was a better way to represent a max, and in fact is. Again, let's just remember some things, but if you want to remember everything, you need to check out the last videos, as in I talk about, well, what minimax is, and much more detail, and I explain what the functions of actions, the specific functions are. So watch my last videos to understand. But again, let's just remember. The mini-X has almost like two artificial intelligence, or two goals. There are the max one, there's max agent. I like to call it the max agent, which it tries to maximize your score. This could be our artificial intelligence. Let's say it's trying to beat a opponent, which could be human or could be an artificial intelligence, which is the minimizing agent, which is trying to minimize the score. Now, maximizing, minimizing the score, again, more detail in last video, but pretty much meaning the maximizing agent wants to win, or the X wants to win, and the circle, which is minimizing agent, wants to win. Uh, Now, here comes the interesting part of how can I represent this. There's like a tree, a node tree per se, which shows. So, for example, here I have a maximizing agent, or better yet, a maximizing action, where I have this green one pointing up as the maximizing, and the red one pointing down as the minimizing action. So let's see of how would the breakdown here. In this case, it's a simple breakdown, not a specific game. I have one node, which is my node, which is trying to make the best decision to maximize my score. And I have the options for choosing against three minimizing actions. Again, or game of tic-tac-toe, or in this case, the minimax algorithm tries to determine how a person would try to, well, would try to calculate what it would do. So in this case, it's pretty much in this situation, what do I do? So let's see the scores. I have some score here. I have 5, 3, and 9. So I can say for certain that the the score I can choose here is 9. After all, this is the maximum score there is here. There is the maximum score I can choose. And so this doesn't depend much on the action, but it will here in this situation depends much more, because most of the time the artificial intelligence is trying to, well, look what the action of the other would try to do, especially in the minimax algorithm. So in this case, in this algorithm, we can say, for example, that this everything here is a simulation from the minimizing action, and it wants to see what's the lowest action it can do. So in this case, we had this last node, which is 9, but I have also a second option where I can choose between 9 or 8. It's the minimizing agent, of course, I would choose 8 over 3, really. So this is where things become interesting, because that's kind of the point. This node is pretty much how artificial intelligence would see. Not in the case of nodes, it would see more as math, but in the situation where it will try to look ahead. So think of what the opponent is thinking. So you create a ginormous tree with pretty much all the possibilities. There's no restraint. We literally create the whole game with every single possible action inside of, well, our computer, and then it will try to make a move for it. So for example, in this situation, it's also probable this node here would be a node from our maximize agent, and it was trying to see what's the possibility between these. Well, again, minimax. Now the minimax here, there is no restriction, so it's very interesting indeed. And again, let's just remember that we're using minimax. Now let's categorize a little bit more minimax as we didn't do last time. So in minimax, given a state, I can pick, if I'm max agent, I will pick an action in the actions function, meaning I will do an action or pick an action that produces the highest value of the mean value result from state action. Pretty much meaning I'm trying to see what will the mean or the minimizing agent will do, so the minimum value that will result from the min action or the minimizing agent action of a state and action, or pretty much the result state. Meaning I'm trying to look ahead. I'm trying to see what would be the best possible choice my enemy or my opponent could choose, so I would choose ahead and try to make it better, or in this case, as a maximizing agent, the highest value possible. And actually, the minimizing agent will do the same thing, just in reverse. It will try to pick an action that produces the smallest action, the smallest value in, well, the possible actions of the maximizing agent. So it's a game of not guess, but you will try to calculate what the opponent would do over and over. So if you could see a function like this, we would do, for example, in this situation, this is pretty much what we can do in I would call this, and as the professor called, I like the name of demicode or semicode. It's not exact, it's not a code, but it's what would the logical process would be. If my function of max, meaning I'm the max player and I'm trying to search for the value of a state, in this case, just if it's terminal, then I return utility. Meaning, if it's the last, meaning the game is over, then I return if it's either a tie, either a win, which is good for me, maximizing agent, or a loss, which is bad for me, maximizing agent. I define a v, which could be is a variable, to minus infinity, and the reason why I do this is because with the minus infinity, there is nothing lower than minus infinity, meaning any action that, well, is lower than this is better than, of course, because there is nothing lower than this. So any action higher than this is better. So inside my actions, I will search for a action in my action state or my actions function, and I will now define that my variable is maxed, variable mean value result state action. I could say a better term, much better term, that, well, variable is now the my max value, or the max value of my minimizing agent possibilities, and then I return my variable. I will now play my action, and this applies the same thing, just reverse. Minimizing value, trying to search the lowest. The now it's positive infinity, meaning everything is lower, so everything is better. This ma here is just maximum. Now I will look at it here, but, well, it's a lot of process, really. And if you look at, for example, a game like this, our process would be something like, for example, in this case, I will break down my tree. In this case, let's see a game which has three possibilities. I need to pick between three. In this case, I am maximizing agent, and I'm seeing what the minimizing agent here has under pretty much what it will do. In this situation, I have here nodes of 4, 8, and 5, which means that the lowest value possible here is 4. Now, why this? Why wouldn't you say like 8 or 5? Well, because this is what artificial intelligence is trying to do, or in this case, the minimizing action. The minimizing action is trying to, the minimizing agent or the minimizing agent's actions. We try to minimize as possible. And what we want to do is that we want to guarantee that our choices are the best, even if the opponent does the best possible moves. So, yeah, our opponents perhaps it might not be well programmed. It might choose 8, but it will probably, or better yet, the maximum value I can ensure here is 4, because well, considering does my opponent does everything perfectly, then here's 4. Now if I apply the same logic here for everything, I have a 9, a 3, and a 7, meaning the maximum value here is 3, and the next tree or next part of this branch, it have values between 2, 4, and 6, meaning the lowest possible value, which is the value considering, is 2. And between these, of course, a maximizing agent will choose 4. Even if, for example, in the middle tree, this is the best possible value, which is 9, it will still choose 4 because at least I have a guarantee for. Here I perhaps have a 9, I perhaps have an even lower number, 3. So we don't want to risk it too much. So since we're trying to do everything at the maximum possible insurance that this will work, then here it is. I have a 4. Now this tree is very interesting because we always ask this: is this optimal? Is this situation, is this minimizing, or in this case minimax function, is optimal? Well, I wouldn't say so. I would say really it's not optimal at all. After all, I need to calculate every single thing, or I need to look out in every single tree to know what option I need to go with. It's kind of weird, but we can do a little bit better. We can optimize this. Let's just remember, for example, that we have a game of tic-tac-toe. After all, remember that this is just a representation of minimax, and well, a minimax algorithm could play a game of tic-tac-toe. A game of tic-tac-toe has 255,168. So I said 62 last time. 68 possible games, or better yet, possible states. Meaning, well, there's a lot of things. These last three here would have 255,168 nodules. After all, they will try to consider from each other. But many of them are reductant because they are bad choices. So if we have a way of simplifying this value, as when it will ignore a value that is lower than my current value, then well, it would be better. So well, we call this a very interesting thing. Now I will show you, for example, how it works. Then I tell you the name. Here I have some nodes. Again, the same puzzle. But here, let's start again with my node from here. And it will play out the same. You'll see the nodes 4, 8, and 5. In this case, we choose 4 because it's the current here in this situation. It didn't choose 4 for now, but it sees that the best possible way of what could happen here is 4. Now, here where things get interesting. As you will see the second node, we'll see 9 and 3. I don't need to look anymore. because, well, here in my tree, I know the value is 3 or less, meaning my next node here, the node here, could be higher, but it does not matter. Uh, since after all, this is 3. Here, inside here is 3. And, well, it could be less than 3, meaning this could be 2, but since my value here is still higher, then there is no need to check. I have no reason to try to look at this, because, well, after all, I have 3 here, so it's already a worse decision. And this becomes even more apparent with the next node. As it starts with 2, then I do not need to look more at this particular branch. After all, I know the value is at maximum 2, meaning my maximum guaranteed value is 2. Does not matter if maybe this nodule is a billion, or 1,000 or 10. It does not matter the value of the next. If my opponent plays well, efficiently, so it plays knowing the rules pretty much, it would choose 2, so it's already worthless to me. And again, I have my choice of 4. This is called alpha beta pruning. Alpha because it's the high maximum value, which is trying to store. After all, I need to store the values to know. Beta from the lowest value, and pruning from the, well, removal of nodes that are, well, useless for me. But here comes the problem, because miniMax itself has a big problem with, even if we apply alpha beta pruning to searching for big problems. After all, we are looking at tic-tac-toe. Even though there are a lot of possible moves or possible states inside this game, it's still nothing compared to a bigger game. Let's say chess. In fact, there is a map made by a person. Okay, this is not. This is actually pretty much hand drawn from the guy. Actually, there are very funny comments if you like. Sorry, comics comments. They're very funny comics if you like math in general. He does great stuff. I have actually reading this for a while, and he made a complete map for optional tic-tac-toe moves by hand. And actually, there's a second part just for the circle. And so you can see that, well, it looks a little complicated, but it was made by a human after all. Maybe it took afternoon to make this, probably less, but also the link is here if you want to see the specific one. But, well, what can I say? This is not much if you consider a game of chess. After all, 255,168 possible states or possible moves is a lot. But we consider a binary game, just as I was telling, like chess, which after 4 moves each, so barely. So in the start of the game, we have 288 billion possible moves, and if we have just from the start of the chess game, we will have 10 to the power of 29,000 possible moves. Now, this seems like a lot, and this is absolutely understandable. This number of possibilities is insane. In fact, if we ponder a bit about this number and we compare it, this number is so huge that if we took the number of atoms in the universe, of fundamental particles in the whole observable universe, it would still be much, much lower. We took the age of the universe, of the current universe, in in phantom seconds, which are a quadrillion of a second, meaning each second a quadrillion phantom seconds is passed. So if you take 13.77 million years in phantom seconds, meaning I will multiply this by quadrillion, it will still be less. And if I, well, if I take the whole, um, a Google years, which would be the number of years so to a new universe to, die pretty much, as in where every single matter will decay, as if proton decays, that is, because again, our universe doesn't come even close to this number. It will still be less than the number of possibilities of, well, what we could do in a chess game. Oh, I noticed that my sign here was, wrong. Yeah. I should put this on the other side. But anyway, it's still. I think you get message across. This, in I would say, even though the professor say that in a reasonable amount of time, I don't know what it's talking about. For a while, for what I know, it's, not impossible, but it would take probably more than the age of the current universe to process by minimax, even if you're extremely proficient. Now, I can be extremely wrong. Maybe computers are much more incredible than I notice, and they can do something like this. Well, what can I say? It's still a lot of processing. And again, we ask, is this optional? No, it is not. Even if I remove the, bad choices per se, we still need to process a good chunk of this number, of this ginormous number. And so we have come to something like a depth limited minimax that allow us to limit the depth it can go. After all, minimax will try to go this far. We will try to process the whole game. We try to guess pretty much the whole game before it makes even a single move. So if there is a way we can limit this, meaning if there's a way with, instead of taking the whole game apart, just take for example the next 5, the next 10, the next 15 steps of our opponent, then we make a move, but becomes a problem. After all, the minimax is doing all of this because it needs to use its function utility to see if it's an actually good thing or not. So we need to create an evaluation function, meaning pretty much that, well, it will try to see what's the best function or the estimated a utility function of a certain step. For example, if I have a game which a game of again a game of, let's say, tic tac toe. Again, it's an easy game to represent, and I have, for example, that point as where I have a, well, I have a single a point. For example, I have, I don't know what's called. I don't know the names, but I have x as my maximizing value. I'm maximizing agent. Sorry, it made a way as there is, like, for example, this move, as where even if the circle blocks one, I can still win. But it's not an end game yet. After all, it didn't finish the game. So I need a way of my artificial intelligence to give a number, pretty much a break number. We will give a broke number. So instead of 1, we give, for example, 0.9, 0.1, uh, minus 0.3, and so forth. So it pretty much will be a gradient between 1 and minus 1 and 0, of course, in the middle. And we will try to see what's best. After all, unless I finish the whole game in the first step, and I pretty much finish the whole game, each single uh, step I try to take, it will take forever. So doing this, it's, well, more than enough. Then what would define a good artificial intelligence from a poor one is, in fact, this evaluation function. This is pretty much becomes the most important thing, because it's not a certain thing, really. It's not exactly certain doing, it's a higher possibility. It's pretty much like in the Note 3, I can choose between 4 and 3, but in the Note of 3 there's a 9, which is the max possible. There's an 8. I need to choose what's the best possibility of each. And so we finish our video actually. I hope you like it, and if you did, check out the other content. After all, to understand this, you need to check out the content, or pretty much won't make any sense. Not just that, but subscribe and hit the notification bell so you'll not miss the next video, which is about of how artificial intelligence can know. Or, well, I haven't watched it, so spoilers alert, I think, especially for me. But will be very interesting indeed as I journey through learning artificial intelligence in Harvard. Hope you like it. You can try to, well, access the course down below. Not sure if you can still subscribe to it, but you can try. It's free and online, of course. And I think I see you tomorrow. Goodbye. Woo!